All right, everybody. Thank you for coming back. I appreciate you being here. Just a final reminder, I guess, that we will have an exam tomorrow evening. So running at the same times that we ran last time, which I think nominally for people will be beginning at 6:30. But the times are posted on the My Courses website. If you arranged for separate times due to accommodations or conflict with me, then I believe that I have communicated that with you when those times will be. So if you did not get an email from me, or if for some reason you got it but can't find it, shoot me an email and I will finalize that with you as soon as I can. So just like last time, we will have 10 multiple choice questions, which will be accessed through the quiz portion of my courses, and 2 long answer problems, which will be accessed in the assignments, which used to be called Dropbox, I guess. So that's where you'll see where the questions are and also where you'll upload the questions. If there is any difficulty, I will be monitoring my email during the exam, so you can always shoot me questions then, but hopefully we won't have any technical problems. I believe that I fixed the issue that we had last time so that we won't have that same problem again. Does anybody have questions about the examination tomorrow evening? Sounds good. I will still have office hours tomorrow at 4:00 p.m. So you can ask questions if you run into questions about material as you're preparing. That's the last time you can see me before the examination. So this is what we have left. So we're 5A right now. So today we're going to go through what we call the Brayton cycle, which is essentially how natural gas power plants are run. But then also we'll see that it becomes the core of turbojet engines. So what we're going to do today is talk about the Brayton cycle and then ways we can improve efficiency of Brayton cycle. So really focusing on natural gas power plants today. And then I'll leave us some time, some open time if you have questions about the exam. But again, you're obviously welcome to stick around for that. Ask any questions you have, but I will also have office hours tomorrow at 4. And then on Thursday, we'll introduce this idea of using this same Brayton power plant, but in an aeroplane. So basically, how do we make a jet engine, or at least a type of engine called a turbojet engine? And then we'll get into heat pumps and refrigerators. I think we will finish with new material on Thursday, and then next week, which is the last week of the class, we'll have 2 sort of open classes. So maybe at the end of next class, maybe I'll take a poll on what problems we might like to look at in that review, and then I'll ask students to sort of bring questions in so that you can kind of, complicated questions, so you can sort of see me struggle, see how I would do it, how I would apply this kind of method that we talk about in sort of real time, right? So that's kind of the overview of what's left. We talked about this last class, but again, I think as we keep introducing new cycles, I think it's important to kind of remember that there's a bunch of different questions that we want to ask for all of these cycles. And if we think about it this way, see, this is, I think, one of the first things that I said to you guys is that a lot of people don't like thermodynamics in mechanical engineering. And I think part of that is because they try to memorize everything. So I think people who look at all these different cycle types as different things and try to memorize all the different answers, at least for me, it would just be too much to do. So instead, I like to think about this overarching process that we're going to apply to all of these thermodynamic cycles. So we're going to ask, how do we characterize the cycle? This is always energy benefit divided by energy cost. If it's a heat engine, we call it a thermal efficiency, so we get this scripted eta. right? But if it's a coefficient of performance, for heat pumps we'll get gamma, and for refrigerators we'll get beta. We talked about that a little bit in the ideal sense. That's something that you might see on the midterm tomorrow, but we won't talk about that in terms of a cycle analysis, component by component, until next class, right? And then we got to ask ourselves, what happens to the mass inside the cycle? Is it like an assembly line where the mass is moving from component to component to do a different job? Or is it like the internal combustion engine that we just talked about, where all the jobs are really happening in the same place? So the mass, we assume anyway, is closed inside the system, that no mass comes in or out. After we know whether it's open or closed, that lets us write down the right equations, right? But the equations are general, and to get to a specific solution, we need to do a first law on all the different elements or processes in our cycle. That'll let us find things like net power or heat rate in, right? And then at least sometimes we'll have to do a second law analysis if we're asked something like, is this process possible? That'll give us symbolic solutions. But in order to get numerical answers, we're going to need to know what the fluid is, because this is another thing that I think people don't like about this class, particularly if they're trying to memorize things, is you can have an equation that has delta H in it, but there's like 5 or 6 different ways that we know how to find delta H, right? So what's the right way to find delta H for the problem that you're doing? And I think narrowing in on that starts with what's the fluid, right? And if it's an ideal gas, then you need to know, is it constant specific heat or variable specific heat? And you're going to look for those processes that are going to be isentropic. That's the key to solving those problems. If it's water or something like it, maybe a refrigerant, then you're going to ask yourself, is it a superheated vapor? Is it a two-phase mixture? Is it a subcooled liquid? And, which is kind of new since the last exam, are we going through an ideal pump? Because we have a special way of calculating delta H if we're going through an ideal pump. Once we know what the fluid is, hopefully that gives us some idea of how to go through and fix all the states. So we start to get the numbers, which is good because now we're just collapsing things into a solution, right? So now we take all the numbers because we fixed the states, we put those into the equations that we got. Now we know things like net power and heat rate in. That lets us say, what's the efficiency, the thermal efficiency of the process, or coefficient of performance if we're talking about refrigerators or heat pumps, right? And then sometimes we'll be asked another thing. We could say like, oh, is this cycle possible, right? So what that's saying is the thermal efficiency that you found, is it less than the Carnot efficiency, right? The efficiency of the ideal cycle. And if it's less, well, then that's at least within the realm of possibility. But if it's more than that Carnot efficiency or higher than the Carnot coefficient of performance, then you know that that thing can't happen, right? But again, I think I said this last time, for me, this is still too much stuff to memorize. So I boil all of these cycles down to what's the characterization parameter? Are the processes in the cycle characterized as being open or closed? And what's the fluid? Because I think if I know all 3 of those things, that's really sort of all I need to know to at least get started. Now I might get tripped up. Maybe I can't fix all the states or something, right? But it at least gets the ball rolling, right? And that I think is such a big difference. There's a huge difference between if you go through a problem and kind of miss a couple things or stumble a little bit versus, I turn that page and I see the last page and it's just blank. Because there's nothing I can do for you if you give me a blank page on an exam, right? But if you at least write something down, it's not that hard to get the first 30 or 50% of a problem usually, right? So, if you're lost in thermodynamics class, write down the first law, right? And start to write down some assumptions, right? Because that'll at least get you something. It demonstrates that you know something about what we've been talking about over the last, 4.5 weeks. So today we're going to take this same methodology and we're going to sort of superimpose it on a different kind of power plant, right? Today we're going to talk about natural gas power plants, and natural gas power plants run on something we call the Brayton cycle, right? All these things are named after people, right? So when I took this class, you know, they would have the, you know, picture of some old dude and be like, hey, this guy invented this thing, right? But I don't have those slides in my presentations anymore, right? So when we talk about Brayton cycles, right, typically we're talking about natural gas power plants, right? And at least in 2019, this made up about 40% of the power generation in the United States. Now, obviously, a lot of things have changed since 2019. My guess is that this number has at least stayed the same, probably gone up a little bit, because our general strategy seems to be reducing coal and increasing natural gas, right? And I think that's why we've seen some of the decreases in greenhouse gas emissions here in the United States, right? I think that's a big driver of why that happens, right? So when we look, this is a table from the textbook, right? You know, why do we care about Brayton cycles? Right? Because this is natural gas power plants, right? And like we said, natural gas power plants, kind of a big deal here in the United States. Geopolitically kind of important too, right? Particularly in Europe right now, because they need somewhere to get natural gas from. Right? So about 40% of the energy in the United States is being produced, or is being produced using these Brayton cycles, right? Using these natural gas power plants. Right? So still, you know, why do we care? Why is this interesting, right? Because like I said, part of the reason we've seen this decline in U.S. carbon emissions is because when you look at, both of these are from the EPA, I think, that's Environmental Protection Agency, right? So here, you know, we dramatically decreased gas, or coal, right, and increased gas. Now there's some increase in renewables here too, which I think is good, right? But the majority of this decrease comes from moving from coal to gas, right? And that lowers carbon emissions, right? So the good things about gas turbines, right? They're faster and cheaper to construct, particularly when you're comparing them to nuclear power plants, which are zero emission but have the potential for catastrophic failure, right? We have natural gas that we can burn here in the United States, so this is something that we can get for ourselves, so we're not dependent on some global supply chain to get natural gas into the United States. It's something that we can use both for power generation to keep the lights on, but as we'll see next class, this is also something that we can use for vehicle propulsion. So when we start to talk about things like how do we keep jet planes in the air, we'll see that the Brayton cycle is an important part of that as well. But like all things energy, it's not all positives, right? So this is still a fossil fuel, so there still are carbon emissions, right? So it's not a zero carbon footprint technology, right? We have some difficulty getting natural gas out of the ground, right? So this is a process called fracking. I think particularly if you live around here or in a state like Pennsylvania, you've probably heard a lot about this and how, you know, when we do this well, I think it works pretty well, but there's some evidence of us not doing it well, right? So that's, I think, why we need smart, young, capable engineers, right, to get out in the field and to solve problems like this, right? Because all of these energy generation problems have downsides, right? So how can we try to sort of implement this all of the above type strategy to try to maximize the benefits while minimizing the downsides, right? So how do these gas turbine power plants or Brayton cycles work, right? So normally these are open to the atmosphere when we're talking about a natural gas power plant, right? So in that way, they're kind of like your automobile, right? They're taking air in from the environment, they mix it with fuel, they do some stuff to it, and they get power out. But you might notice that this is like an assembly line type process, right? We're taking air in, we're going through a compressor, that's like a pump, going through a combustion chamber, that's like a steam generator in a Rankine cycle, going through a turbine, which is like a turbine, although now we'd call it a gas turbine, whereas in a Rankine cycle we'd call it a steam turbine, and then there's some exhaust air, right? So it's like a heat engine, which means it's like a Rankine cycle and it's like an internal combustion engine. But here, usually, well, always when we do the analysis, when we think of each individual process, it's an open system, right? So we're going to use the same equations that we used when we were talking about Rankine cycles, right? But like an internal combustion engine, the working fluid, although it's really some complicated and changing mixture of air and fuel, right? We're going to say that the working fluid is just air, right? So it's a little, it's mostly like Rankine cycles, right? Until we get to the, right? So if we say, what's the energy benefit? It's work out or power. What's the energy cost? It's heat in or heat rate in, right? So where you're going to talk about thermal efficiency, right? When we say what happens to the mass, oh, it's going to be open systems. We're going to use the same equations that we used for Rankine cycles. But when we start to solve those equations, put numbers in, well, then what's the fluid? Oh, it's an ideal gas. So then it's going to be a little bit more like an internal combustion engine in terms of how we fix the states. Right? So typically what happens in a gas power plant, we have air that's coming in from the environment. Right? And it goes through a compressor, right? So we're putting work into the system. We're increasing its pressure, and because it's a natural gas, right, we're going to assume it's an ideal gas. So as we increase the pressure, the temperature goes up too, right? But then we mix the air with fluid in the combustion chamber, and we are igniting that air-fuel mixture to generate heat, right? So this is, we think of this process as adding heat into the system. And then we go through this turbine, right? So now we have the spent air fuel mixture, right? And it goes through the turbine because it's expanding because the temperature got higher, right? So it wants to expand. We expand it over some fan blades, right? And that turns this shaft, right? Now, the cool thing about this Brayton cycle is that the compressor shaft and the turbine shaft are often the same shaft, right? So it's the turbine that's spinning that's running the compressor, at least once you get the system going, right? So that's kind of a neat thing. Unlike, a steam generation plant, a Rankine cycle, I think of it more like the turbine is producing power, so there's some wires that are coming out that are, electrical power, and you're plugging the pump into the wall so that, you're sucking power off the grid. Right? So this is always running, right? So once you turn it on, you're always sucking air in and exhausting air out. So there's always intake and exhaust sort of continually inside this process. Right? This is just what I was saying before, that the shaft or the turbine and the compressor are mechanically coupled. So as the turbine is spinning, part of the power that it's generating is automatically going to drive or to overcome the load on the compressor. Right? Now the rest of it, right? We probably want to make friends with electrical engineers because they're going to put something like an electrical generator on this spinning shaft, and that's going to, take up the rest of the load that's being produced by the turbine here, and that's going to generate electrical power that we can put out onto the grid. So where do we get heat, right? Normally, this is from burning natural gas, right? So that's why most Brayton cycles that we think of, sort of, especially with the increase in the use of Brayton cycles, it's coming from natural gas power plants. But it doesn't have to be, right? So the number one driver here is this external combustion of fossil fuels, right? So that's natural gas. But anything that's generating heat, you could also use, right? If you're just adding heat, provided that the heat is sufficient to drive the cycle, you could run one of these Brayton cycles. So you could have something that's generating heat, right, from some waste heat from some industrial process. Maybe even a Rankine cycle, right, has a bunch of waste heat. Maybe you're taking that heat in and you're running one of these cycles with that. Now because you're not necessarily burning a fuel, so you're not consuming oxygen, you could have a closed system like this. That's what this is showing here, that there's this closed loop, right? So we're going around and around and around. But ultimately, the analysis doesn't change whether or not you have that heat exchanger that's getting rid of the heat transfer, or at least the analysis for the thermal efficiency, because thermal efficiency only cares about heat rate in and not about heat rate out. Right, so you can get heat from solar, or solar thermal energy. So this is the idea, like, something like if you had that deflector that's collecting heat and bouncing it back into some certain place, right? So that you're generating heat that way. So again, you can use this to cool something like a Rankine cycle that's maybe powered with nuclear or with coal potentially, right? So some of these can be closed. If it's running through a closed system, right, then it's the same thing, right? So the air, if it's a closed system, you just have to pick an arbitrary starting point. It's a little weird because in the Rankine cycle, we picked the arbitrary starting point to be before the turbine. But here we pick it before the compressor. I think that's because in the open system, in the sort of more traditional way that we run these, we're pulling air in from the outside. So that's kind of where air starts its journey in the cycle, right? So we go through the compressor, the heat exchanger, the turbine, and then there's some other heat exchanger where we're extracting heat, right? I just like this. I think this was from the textbook animations, but I kind of like it when the dot runs around the cycle, right? Here the heat gets transferred out to the environment into some kind of a heat sink, right? So something is pulling the heat away, but in this picture it doesn't tell us what it is, right? So when we look at this, this is a Brayton cycles versus Rankine cycles. When we look at this compared to the Rankine cycle, which is kind of like our, I guess our benchmark, because it's the first one we used, right? And we look at our 3 questions, it's still a heat engine. So it's still net power divided by heat rate in, like the Rankine cycle, and unlike the internal combustion engine, it's open systems, right? So that means that our equations are going to be rate equations. We're going to be dE by dt equals a bunch of stuff, right? We're going to have to think about mass flow rates. Although thankfully we don't split the mass in a Brayton cycle like we did in the Rankine regeneration cycle, right? The difference between a Brayton cycle and a Rankine cycle comes when we ask the question, what's the fluid? Because with a Rankine cycle, what's the fluid? The answer was water, right? So we were thinking, okay, now what's the phase? Is it an ideal pump? But now, in a Brayton cycle, the working fluid is air, which we're going to treat as an ideal gas. So now I'm going to say, well, where's the isentropic processes? Now, unlike the internal combustion engine, we're not going to assume that everything is always ideal, right? But just like a Rankine cycle, remember we had a real pump and an ideal pump? Well, I can have a real pump and an ideal compressor, so I could give you some kind of isentropic efficiency here, right? And I can have a real turbine and an ideal turbine. So those isentropic relationships are still going to be important, but because when we do the first law, we find that the compressor and the turbine are probably going to be isentropic if they're ideal, right? So we'll use that isentropic efficiency to get the real outlet, right? So the difference here is it's like the Rankine cycle up until you're finished your symbolic solutions. But then when you start to put numbers in, the way you fix the states is different because the working fluid is an ideal gas. So it's an ideal gas. So just like, or at least similar to an internal combustion engine, we're going to run that air standard analysis, right? So we're going to neglect combustion. We're just going to pretend heat's coming in, heat's going out. We're not burning anything. The gas is not changing. Unlike the internal combustion engine, we're not going to assume that the systems are closed here. We're going to say they're open systems in each component. We're not going to say that all processes are reversible, although we may sometimes talk about reversible or ideal turbines and compressors. The working fluid is going to be air, which is an ideal gas. We're not going to account for the fact that really the chemical composition of the gas is changing because there's this combustion reaction that happens. And then sometimes we're going to say it's variable specific heat, but sometimes we're going to say it's constant specific heat. Now, on an exam or when you're reading a problem in the textbook, it might say the words cold air standard analysis, which means constant specific heat. So this is our Brayton cycle. And our cycle runs from state 1 going into the compressor to state 4 going out the turbine. Now, in many real applications, this heat exchanger here doesn't really exist. Or at least it's not like a manufactured component, right? Because it's kind of like the Earth is our extra heat exchanger here. Because what we do is we're pulling in fresh air from the environment, right, at a low temperature, and we're exhausting spent air fuel mixture, right? So it's probably got some carbon dioxide, some more carbon dioxide in there. Hopefully it doesn't have things like carbon monoxide or nitrous oxides or anything in there, right? And we dump that out into the environment. And the temperature is higher, right? So you don't want to put your intake right next to your exhaust, right? Because you want to be pulling in fresh air. Now, because it's still heat engine, the energy benefit is still net power. The energy cost is still heat rate in. Right? Just like the Rankine cycle. And like the Rankine cycle, another way we can characterize this cycle is we can talk about a back work ratio. Right? Now remember, the back work ratio is sort of recognizing the fact that the power plant is the first consumer of the power from the power plant. Right? So that in order to run the power plant, you have to run the compressor. Right? So this is the compressor power divided by the turbine power. Now it's interesting here because Rankine cycles are less efficient than Brayton cycles. So Brayton cycles have higher thermal efficiencies. Right? And we talked about sort of the main downside of the Rankine cycle, or at least one of the downsides of the Rankine cycle, is that you have to cool that water down, right, from steam back to liquid water, which means you lose a lot of heat. Right? To cool the fluid down in a Brayton cycle when it's ideal gas, it doesn't need as much cooling, right? So that means you tend to get higher thermal efficiencies. But it's weird because the backwork ratios are higher. So mechanically, you end up using more of the power that you develop in the turbine just to run the system, right? So your backwork ratios are higher. And the reason for that is that it turns out that it doesn't take as much power to increase the pressure of a liquid like we did in the Rankine cycle, because there you're dealing with that incompressible fluid, right? The molecules are already really, really close together, right? But as you go through the compressor, it takes more energy to increase the pressure of that air or ideal gas because it's a compressible fluid, right? So your thermal efficiencies are better in Brayton cycles, but your backwork ratios are worse. Okay, so that's great, right? We know that we're looking for W.net over Q.in, but how do we get W.net and how do we get Q.in, right? This comes down to that second question, right? What happens to the mass? And we know that we're talking about open systems as we move through the cycle here, right? So, systems will be at steady state, right? They're always one inlet, one outlet, or at least we never split the mass in this particular cycle. We're going to always neglect kinetic and potential energy, at least for the power plant version of this cycle. That'll change when we talk about turbojet engines, right? And then components will either be adiabatic if we're looking for power generation or power consumption, or they'll be passive if we're looking for heat rate in or heat rate out. Just like for Rankine cycles, we'll neglect friction losses. So anytime we're adding heat, we'll assume that happens at constant pressure, or removing heat, we'll assume that also happens at constant pressure. And we won't account for any heat or pressure losses in the lines that connect the different components, right? So the outlet of my combustion chamber, I'm going to assume that the state of the fluid thermodynamically is exactly the same as it is at the inlet to the turbine. Even though there's probably some losses in the system, we assume that they're small enough that we don't care about them. That's going to give us equations, or at least equations that have the approximate shape that we're used to from Rankine cycles. that if I'm trying to find power, we're going to have m dot times h in minus h out. Turbine power will be positive, compressor power will be negative, so I add those things together to get net power. And if I'm looking for heat rate in or heat rate out, that's going to be m dot times h out minus h in. So that's good because that'll give me symbolic solutions. Right? But then I got to ask myself, what's the fluid? How do I fix the state? Right? This is where we differ from a Rankine cycle analysis, because the working fluid here is air, right? Which we're going to assume to be an ideal gas. So if it was an ideal cycle, the TS diagram is going to look like this. I go through the compressor, that increases my pressure. I go through the combustor, that increases my temperature at constant pressure. And then I go through the turbine, that brings my pressure down. Right? And then this process from 4 to 1, that's cooling the fluid off. Sometimes there'll be an actual component in there that's cooling the fluid off. But oftentimes we're really just exhausting this air to the environment and pulling new air in. Right? So power goes in at the compressor. That's 1 to 2. Heat is added from 2 to 3. Power comes out at the turbine. And then heat gets rejected as I move from 4 to 1. Even if that heat exchanger is just sort of the air that we're all breathing. Right? Now, it's a good thing to know both the PV and the TS diagram. But typically, for cycles that have open components, what I really want is the TS diagram. I think is more valuable. Right now, when we talked about Otto and diesel cycles that were closed processes, it was the PV diagram that I think is more useful. Right? But it is nice to know what that PV diagram looks like, because then you can remind yourself that because there's no friction losses while we're adding or removing heat, we're going to assume that that happens at constant pressure. Now, the key to any process where the working fluid is air, when you start to fix states, you have to know where the isentropic processes are, or at least where they could be if everything was ideal. And those will be the components that have to do with power generation or power consumption, right? So as you go through a turbine or as you go through a compressor, those have the potential of being isentropic, right? Those are the places you're going to use some equation with K in the exponent if it's constant specific heat, or some equation with PR or VR in it, right, if it's variable specific heat. We talked about this a little bit for internal combustion engines, right? But if everything was ideal, then the area inside your cycle on your PV diagram equals the area inside your cycle on your TS diagram, right? And that net work is equal to net heat. This is kind of neat, and we'll talk about it a little bit more later, but ultimately, you're going to have, say, some maximum temperature that your turbine can take, right? So ultimately, your turbine's going to eventually melt at some temperature. You don't want to get that hot, right? So you have a design decision that you can make, right? You can have this cycle from 1 to 2 to 3 to 4 that has a low, this is hard for me to say compressor pressure ratio. So that tells us what the change in pressure is across the compressor, right? But you could also have a high compressor pressure ratio where the compressor gets you up to some high pressure, but you're still limited by this maximum temperature, right? Now, in this case, cycle A, which is from 1 to 2 prime to 3 prime to 4 prime to 1, right? That has the greater compressor pressure ratio. So you can see we get, right, because each one of these lines is a constant pressure, and from 1 to 2 is a shorter distance than 1 to 2 prime. So this is the bigger pressure difference, right? That has bigger thermal efficiency. right? So the higher compressor pressure ratio gives you bigger thermal efficiency. But cycle B has more net work developed per unit mass, right? So the area of cycle B, which goes from 1 to 2 to 3 to 4, maybe you can just see by your eye, but the textbook tells us that has more area in it, right? Which means there's more work. So there's a trade-off here, right? As is often the case, just like if you're choosing between, a Prius or a Bugatti, one of those is going to be more fuel efficient, right? And one of them is going to give you more power, right? So as is often the case in mechanical engineering, really any kind of engineering, you have to judge between trade-offs, and it'll depend on your application, right? So as an engineer, part of the reason that you'll get paid a first world salary here is that you're the person that's going to make these decisions, right? So if you're thinking about something like an airplane, trying to get something that's heavier than air to fly through the air, your main concern is power to weight ratio. It's not like you don't care about efficiency, because you will save your company a ton of money if you can make your turbojet more efficient, right? Even very small efficiency gains can turn into big numbers with dollar signs in front of them, right? But you might be mostly interested in maximizing that power to weight ratio, right? But if you're talking about a power generation application, maybe you don't care about the weight quite as much. And because your power generation station is virtually going to be on forever, at least for its usable life, maybe what you want to do is maximize your thermal efficiency, right? So that maybe you don't care as much about the weight, which is related to the cost probably of manufacturing, right? Getting it up and running. But you maybe save that in the long term by improving your thermal efficiency. And you don't have to make your power plant fly, so maybe you're a little less concerned with the weight there, right? So this is the kind of decision that you might face during your career as an engineer. Okay? Now, I've said a couple of times that when you're thinking about these cycles that have air as the working fluid, it's really important to know where the isentropic processes are. Of course, the real answer to that is that there are no isentropic processes. So really, it's where could the isentropic processes be, right? They don't really exist, but anytime I'm talking about a component that doesn't have heat transfer related to it, right, then I could have an isentropic efficiency. These equations are the same as they were for the Rankine cycle, and they're on the equation sheet that I made for you, right? And you can make your own equation sheet. But if you're talking about turbine efficiency, then it's going to be the real turbine power divided by the ideal turbine power. But if you're talking about compressor efficiency, it's going to be the ideal compressor efficiency divided by the real compressor efficiency, right? It's always the bigger one that goes on the bottom. And when you're talking about a turbine, the fact that it's not ideal robs you of power generated, right? It's because you're reducing the benefit of the system. But when you're talking about a compressor, the fact that it's not ideal, the way you overcome the friction in the bearings in your compressor is that you have to put more power in, right? It's a cost to the system. So here it's the ideal compressor that minimizes the cost to the system. So, from this, we can get some equations, right? But again, don't memorize these equations. Memorize these ones. Because as the cycle gets more and more complicated, the turbine won't always go from state 3 to 4, and the compressor won't always go from state 1 to 2. Okay, so now is the point where we're going to do an example. So here we have so this is a Brayton cycle, right? It's just a normal 4-component Brayton cycle. That's all we know so far, right? And it tells us that everything is isentropic, which means ideal, right? So we're going to be asked how to find the net power per unit mass flowing through the system and what's the thermal efficiency. And all they tell us is the temperature and pressure at the inlet, the pressure at the exit of the compressor. So this is like it might also tell us the compressor pressure ratio is 8 here, the high pressure divided by the low pressure. And then the temperature at state 3. So can we solve the problem? Okay, so the first thing that we want to do, well, first maybe I'll go through, even though they tell us this, maybe I'll draw the TS diagram too, right? Because maybe we wouldn't have this right here, right? So the first thing that I always want to do if I have to draw a TS diagram is I want to count up the number of turbines and the number of compressors, the maximum here, right? It doesn't matter which one that I take because they're the same. And then I add 1. That's how many pressures are in my cycle, right? So I'm going to draw one constant pressure line. This is like, remember when we did Rankine cycles, right? And we had a constant pressure line that looked like this. We're just like way the heck up here. So it's a line that's going up as we move left to right when we talk about a constant pressure line. So this is P1. And then we have some other constant pressure line up here, P2. I start at my compressor, which is at the low pressure. And here, because my compressor is ideal, I have a vertical line up over here to state 2S. Right? I could draw this as a constant line here. And then I'm going to add heat. And that's going to keep me at the same pressure, but increase my temperature to state 3. And then I'm going to go through my turbine, which is also isentropic, to 4S. Right? And when I think about this, I'm adding power at the compressor. I'm harvesting power at the turbine. I'm adding heat in the combustor. And then I'm rejecting heat down here from the exhaust. So that's how I think about drawing a TS diagram. Does that kind of make sense? Because you might not be given one when you get to the final exam, right? And this idea here of knowing how many pressures, you can use that for Rankine cycles too, which might be important on the exam tomorrow. Although remember, the exam tomorrow only goes up to the 4-component Rankine cycle. So there'll only be 2 pressures if it's a Rankine cycle. So net power, right? So net power means that I want to know what's going on in the compressor and in the turbine, right? So, but for all my components, I'm going to say that they're all at steady state, that they're all 1 in, 1 out. So the summation signs here go away. We're going to neglect kinetic energy changes and potential energy changes. Right? And then for the turbine and the compressor, we're going to say that they're adiabatic. Once we get to the combustor, which we're going to need for the thermal efficiency, we're going to say that W dot is equal to 0. But what this is going to tell me for my turbine and my compressor, so W dot is going to be M dot. So the other thing that I know here, which sometimes I don't write this down, right? But I know that dm by dt is equal to the sum of m dot in minus the sum of m dot out. But I said already for all of these components, they're all steady state with 1 inlet and 1 outlet. So that means each component m dot in is equal to m dot out. And since they're all arranged in series, and I'm not splitting the mass anywhere, there's only one mass flow rate inside my cycle. Does that part make sense? That will be the same if you get a Rankine cycle with 4 components on it on the exam. So if I talk about a power, right, then this is going to be m dot times h in minus h out, which means that the compressor power is going to be m dot times h1 is the inlet and h2 is the outlet. I guess they're not labeled here. 1, 2, 3, 4. So this is h1 minus h2. The turbine power is going to be m dot times h3 minus h4. And it wants net power per unit mass, right? So I know that my W dot net is going to be the sum of all my turbine powers, which I expect to be positive, plus the sum of all my compressor powers, which I expect to be negative, right? And then if I'm going to divide by the mass flow rate, then I divide those terms by the mass flow rate too. So this is going to be my turbine power, right? So this is going to be m dot over m dot times h3 minus h4, which I expect to be positive, minus m dot over m dot times h1 minus h2, which I expect to be negative, right? But this is just 1 in both of these cases. So now I know that w dot over m dot is going to be equal to, if I put them in order, oh, this should be plus, I'm sorry, right? And this is a mistake you could make, right? So what I did was a double negative here. I didn't trust the first law. That was the mistake that I made here, right? So I wrote it down correctly over here that I'm supposed to add these things together, but I know this one's supposed to be negative, but I subtracted it here. That would make my net power more than my turbine power, which I know is wrong. So hopefully I would have caught that. If I didn't catch it now, hopefully I would have caught that by the time I actually put the numbers in, right? Because one of the checks you can do is that your net power has to be less than your turbine power. So this is going to be h1 minus h2 plus h3 minus h4, right? In this one, we expect to be positive. In this one, we expect to be negative. Okay, but the other thing, so this is my one symbolic solution for part A, I think it is. Part B, I think what they ask us to find is my thermal efficiency. And the good news here is that I'm already halfway there. You might find this on exam problems, where first I'll ask you to find the net power, then I'll ask you to find the heat rate in, then I'll ask you to find the thermal efficiency. I think the textbook does the same thing, right? So B, this is my thermal efficiency, is going to be W dot net divided by Q dot in. Q dot in, I get from my first law on my combustor. When this is 0, I get 0 is equal to m dot, oops, Q dot plus m dot h in minus h out. But I want to solve for Q dot, so Q dot becomes m dot times h out minus h in, because I had to move this term to the other side of the equation, so I multiplied by -1, which means I just flipped the difference. Right, so that's how we get to this equation. So the combustor goes from state 2 to state 3. So m dot, this is going to be Q dot of the combustor is m dot times H3, which is the outlet, minus H2, which is the inlet. We're talking about this process here from state 2 to state 3. So W dot net, or what I can do is I can talk about this as W dot net over M dot divided by Q dot in over M dot. I didn't break any math, right? Because 1 over M dot divided by 1 over M dot is just 1. Right? So this is going to be H1 minus H2, which still I expect to be negative, plus H3 minus H4, which I expect to be positive, divided by, I look over here, my heat rate in is H3 minus H2. And this is my other symbolic solution for part B. How do you feel about that part? This is pretty close to what you do on a 4-component Rankine cycle. The numbers are a little bit out of order compared to the Rankine cycle, but it's pretty close to the same thing that you do, right? So now it tells us constant specific heat analysis. But I'll kind of walk you through how to do both. But it means we got to start fixing states. We already answered this part of the problem. Hopefully I didn't just mess everything up there. Uh-oh. Here's what I'm going to do. So when we do a constant specific heat analysis, really what we're looking for is we want to know the temperature and the pressure of all the different states. So I could write out my own state table. I don't know, maybe that would have been easier. But instead, I'm just going to use the state table that the problem gave me. All right, so the nice thing about this is state 1 is already fixed. So I guess the first thing, because it's constant specific heat, I don't care about H and U. Actually, I wouldn't care about U anyway, right? And I don't care about VR and PR because it's constant specific heat, right? And constant specific heat tells me that all the delta H's are going to become CP times delta T, right? So that means that my equations are going to be a little bit different here, right? So because it's constant specific heat, this is going to become CP times T1 minus T2, which I still expect to be negative. Oops. Plus CP times T3 minus T4. Right? Or I could just pull the whole CP out, right? This is going to be CP times T1 minus T2 plus T3 minus T4. Here I already did the top, right? Is CP times T1 minus T2 plus T3 minus T4 divided by CP T3 minus T2. The specific heats actually cancel in my thermal efficiency, so I really don't care what CP is for part B. All I need are these temperatures. And actually, even though it's an ideal gas problem, so my spidey sense is tingling, always use Kelvin or Rankine, it actually wouldn't matter in these particular problems because we're always talking about temperature differences, at least in these equations. But we'll see as we fix states that's not true. So I could answer this problem if I knew T1, T2, T3, and T4. The beautiful thing here is the textbook, or whoever wrote this problem, told me T1, T3. I just need T2 and T4. CP for air, at least in the metric system. Are we talking about metric here? I don't think it's given here, so you could look it up. I believe that it's typically 1 kilojoule per kilogram Kelvin. For air. You can look it up. I think it's table A20 in the textbook will give you CP and CV and probably K values for various ideal gases at various temperatures. So the nice thing about state 1 is that I already know T1 and I know P1. Life's good, right? Now, state 2. Really, because it's an ideal compressor, state 1 to state 2 is really 1 to 2s. Anytime the working fluid is ideal gas, I ask myself, is delta S equal to 0? And here the answer is yes. That means I can use an isentropic relationship, right? And here, because it's open, I'm interested in equations that have pressure in them, right? So if it was variable specific heat, we would say PR over PR is equal to P over P, right? But now that it's constant specific heat, what we're going to say is that there's a temperature divided by a temperature, and that's equal to a pressure divided by a pressure to the power of K minus 1 over K. Let's see if I put the equations at the bottom here. Sometimes I do that on these. No, but I think I have them in the next problem we're going to do. Unless I deleted them. I believe that this is T2 over T1 is equal to P2 over P1 to the K minus 1 over K. So I can use this equation, right? So now, if I want T2, which is really T2S, it's going to be equal to T1 times P2 over P1 to the K minus 1 over K. We'll be able to check this if I got the ratio right, because as I compress, as I increase the pressure, I should also be increasing the value of the temperature. So while in the equations we have for A and B, for the net power and for the thermal efficiency, it didn't matter whether I was using absolute or relative temperatures, so Kelvin or Rankine, versus Celsius and Fahrenheit. But here it does, because these are not temperature differences now, right? So I don't know T2S, but I do know T1 is 300 Kelvin times P2 is 800, I believe, right? Divided by 100 to the power of K, which is 1.4 minus 1 over K, 1.4. My calculator's over here. So now I can say 8 to the power of, all in brackets, 0.4 divided by 1.4. I get 1.8 times 300 is equal to 543.4 Kelvin. So this is good because now I know T2. Because I know T2, it means that the only thing left that I have to do is find T4. All right, so now as I move from T3, or state 2 to state 3, is delta S equal to 0? No. Right? They told me T3, which is awesome. I love the states where they tell me the temperature, but they didn't tell me P3. But the thing that I remember is that there's no pressure losses. And here, there's no work. So what we assume is that the pressure is constant, so that P2 is equal to P3. So this is also 800 kilopascals. right? And we knew that from when we drew this, right? Because we said from state 2 to state 3, pressure is constant. So this is another thing. If you know how to draw the TS diagrams, it's almost like cheating because the information is already there. I may have told you this already, and if I do, I apologize, but because I grew up in Canada, I had to take French until 9th grade. 9th grade was the last grade, I think, where it was mandated that I had to take French. And after that, because my grandparents are German, I took German. Right? But one of the things that one of my French teachers told me is that if you don't know the answer to a problem, look through the rest of the test because the answers might be there, right? So, you know, if you see a TS diagram for a particular cycle, maybe in a multiple choice question or something, maybe that gives you some information about what's going on with the temperatures and the pressures. Now, as I go from state 3 to state 4, this is my isentropic, or let's say ideal turbine. And I didn't do this for the compressor, but I'll suppose I show you why it's isentropic, right? So if I did my second law analysis, ds by dt is equal to q dot over temperature plus the sum of m dot in s in minus the sum of m dot out s out plus sigma dot, right? So here it's at steady state. It's adiabatic. It's one inlet and one outlet, and it's ideal. So what this tells me over here is that 0 is equal to, remember from conservation of mass, there's only one mass flow rate, m dot times s in minus s out. There's two ways that we can get this, that this equation can be true, right? There can be no mass flow rate going through my turbine, which is kind of boring, right? We probably wouldn't really be analyzing that particular system, right? Or delta S is equal to 0, right? So in the non-trivial case, here delta S is equal to 0, which means isentropic. That means I can use this equation again, but the states are different, right? So here I'm trying to find T4, so I always put the one I'm trying to find on top. T4, I could call it T4S, divided by T3 is going to be equal to P4S over P3 to the power of K minus 1 over K. Or T4S is equal to T3 times P4S over P3 to the K minus 1 over K. Now, one of the things you'll learn in fluid mechanics is that if you're sucking air in from the atmosphere, like we do here, if there's a jet of fluid going into something, its pressure is the same as the atmospheric pressure. And if you have a jet of fluid that's going out into the environment, its pressure is also the same as the atmospheric pressure. So here, P1 is equal to P4. Right, so they didn't actually tell us that, I think, on the state table. But that's, so this is equal to P1. Which means that the ratio on the way up, the compressor increased the pressure by a factor of 8. But the turbine decreases the pressure by a factor of 8. You think when I was up there, I would have got T3 is 1700. So this is 1 over 8 to the power of K minus 1. So that's 1.4 minus 1 is 0.4 divided by 1.4. So you get 1 divided by 8 to the power of 0.4 divided by 1.4 times 1700 is 938.5 Kelvin. So that's how I go about fixing the states. Does that part make sense? Again, I'm looking for isentropic processes. Now, if this was variable specific heat, then anytime I used this equation, T4 or, over T3 is equal to P4 over P3 to the K minus 1 over K. I can't use that if it's variable specific heat. I'm still looking for something with pressure ratios in it though. So there what I'm going to see is PR4 over PR3 is equal to P4 over P3. I'm pretty sure that the top number, that the numbers don't invert, but check the equation sheet. So I would have used this equation, and then remember here, if it was variable specific heat, delta H remains delta H, right? So for state 1, remember, so we have to go to A22. A22 has like temperatures, some stuff, but H, right? And then they're going to have, it even tells you on this thing, it says if delta S is equal to 0, you can use PR or you can use VR, right? There's like an S superscript 0, there's U in there too. But for state 1, we knew T1, right? So then we come across, here we'll get H1, but we'll also need PR1, right? Now we're going to use the pressure ratio to find PR2, right? So because we would have also said that PR2 over PR1 is equal to P2 over P1. So that lets us find, you know, this is given, this is given, this is given, and it lets us find PR2. Then once I find PR2, I interpolate backwards and I find H2. Right. But I'll try to walk through in the next example we do how you would do it with variable specific heat. So with this one I just showed constant specific heat, but it's generally the same, but you use a different relationship for the isentropic process. I think if you go through these notes that I have, I don't remember if I solve it both ways. It looks like I just solve it with constant specific heat, right? So this, remember, we got our equations, right? We didn't know T2 or T4. But we had this isentropic relationship from state 1 to state 2. So I use that to find T2. State 2 to state 3, the pressure stayed constant. And then I used my isentropic relationship from state 3 to state 4, and knowing the fact that P4 is the same as P1, right? So any two states in a Brayton cycle, if they're touching the outside air, the external environment, they have to be the same pressure, right? So then remember, we used our isentropic relationship again. That gave us T4. And then we put the numbers in, right? So here, our net power in this case was 520.7 kilojoules per kilogram. So that's our net power per unit mass flowing through the system. And then our thermal efficiency was 44.8%, right? And we haven't even done anything too fancy, and we're already getting close to half, right? But anytime we have a non-complicated system like this, we might ask ourselves, how do we improve isentropic efficiency? And we'll talk about that after the break. So why don't we come back at 7:45 and we'll go through how we can improve isentropic efficiency or thermal efficiency in these Brayton cycles. Okay, welcome back, everybody. So we talked about Brayton cycles, right? These natural gas power plants. We said that they're a lot like a Rankine cycle, except when we get to the question, what's the fluid, it's a little bit different, right? How we fix the states is more like how we fix the states for internal combustion engines than it was for Rankine cycles, right? But the symbolic solutions look the same. So when we're talking about thermal efficiency, it's still net power divided by heat in, right? It's still turbine powers plus compressor powers divided by heat rate in. I'm still going to use the same version of the first law to get those answers, right? Now, the TS diagram looks different because when I ask the question, what's the fluid, if the answer is air or some other ideal gas, it means I don't draw a vapor dome, right? But if the air is water or something like it, like a refrigerant, it means I do draw a vapor dome, right? But here there is no vapor dome because the fluid is an ideal gas. So what do I do when I go through and solve particular problems, right? Because I say, oh, each component is itself an open system, that unlocks for me this version of the first law. So we said all the components are going to be steady state, one inlet, one outlet, no kinetic energy change, no potential energy change. Then when I look at the individual processes or the individual components, some of them are probably going to be adiabatic, some of them are probably going to be passive. You see, this is the problem when I just to make this one big file, right? So I copied stuff over, and I don't know, PowerPoint, like style files or something must be different. So I apologize that the adiabatic arrow here, this one should be orange, and that one, well, I guess it's a shade of blue, right? So we get these equations that hopefully we're starting to feel more comfortable with, right? That we know and love. If I'm trying to find power, it's m dot times h in minus h out. Turbine power is positive. Compressor power is negative. When I'm trying to find heat rate, it's m dot times h out minus h in. And usually the one that I'm going to be looking for is the combustor heat rate or the heat rate in, right? Heat in is positive. Then I ask myself, what's the fluid when I start to fix the states? And because the fluid is an ideal gas, I fix the states differently than I do for Rankine cycles, right? So when it's an ideal gas, I got to ask myself, is it constant specific heat or cold air standard? Or is it variable specific heat or air standard, right? What's the difference, right? For an air standard analysis, delta H is going to be delta H, right? So if it's variable specific heat, I actually have to find the individual values of H. And when I find my isentropic processes, instead of using an expression with K in the exponent, like we did for the last example, instead I use a pressure ratio being equal to the ratio of these PR values that I find on table A22. Because they're open systems, normally I'll know pressure ratios and not specific volume ratios. Right? Often the thing that I'll be looking for here is PR2, so I can fix then state 2 from table A22. Cold air standard though works just like we did in the last example, that I have delta H, but actually I never care about the individual H's, because for a cold air standard or a constant specific heat problem, I make the assumption that delta H is approximately equal to Cp times delta T. But I still have the problem of how do I find that temperature at the ideal compressor outlet or the ideal turbine outlet, right? So I'm looking for the isentropic process, right? But now for isentropic processes with constant specific heat, I need an equation with K in the exponent. And because they're open systems where I know pressure ratios, I look for the one that has the pressure ratio in it. Right? So we just did a problem, right? And in that problem, we got an isentropic efficiency of 44.8%. Right? So now we're at the point where we ask, how do I improve my thermal efficiency? Right? And we talked about this before, but there's more than one reason to improve thermal efficiency. There's potential monetary savings, particularly in the long run, right? But there's environmental savings too, right? So we need to be able to understand that the best green energy solutions are the ones that that save money too, because those are the ones people want to adopt, right? So just like a Rankine cycle, when we look at our thermal efficiency equation, we can reduce the amount of heat that we put in through something like regeneration, right? We have regeneration here in these cycles too, but it works differently, right? Or we can do reheat, right? That's what we did in the Rankine cycle. But here, remember, reheat kind of gets us more power out. Intercooling is like reheat, but it reduces the amount of power that you put in the compressor. For Rankine cycles, we didn't really care about that because the power to increase the pressure of the liquid was so low that there really wasn't much benefit in trying to reduce that power we put in. But that's not the case for the Brayton cycles. Right, so in a regenerative Rankine cycle, what we did was we tried to use some of the heat we'd already paid for to preheat the fluid before it went into the steam generator. Right? Now for a Brayton cycle, it's kind of similar, but here, what we do is we have heat that's kind of being wasted. We have this exhaust air that's at a hotter temperature than the ambient air or the air in the environment, right? So that means we're losing heat, right? We're giving away something that has some energy locked up in it. So maybe there's some way we can try to harvest some of that heat in that air before we exhaust it to the environment, right? And that's what a regenerator does. Now, regenerators are still complicated in Brayton cycles, but I think they're not quite as complicated as they were in Rankine cycles. Because in Rankine cycles, we split the mass flow, right? Which was kind of a pain. We don't do that in these Brayton cycles. Instead, what we do is we have this regenerator, this heat exchanger here, right? And what happens is, before we get in the combustor, after the compressor, we have this cooler air that's going through over here, right? But we have this hot exhaust gas that we're just putting out in the environment anyway. So what this regenerator does is it lets heat be transferred from the hot exhaust fluid, which is still hotter than this pre-combusted air, right? So we take some of that heat that we were otherwise just exhausting to the environment and we reclaim it, right? So that means that we burn a little bit less natural gas in our process, right? So we have this cold air that's going through, right, pre-combustor, and this hot air that's being exhausted from the turbine, and they transfer heat. Now, we can't get all the heat out, right, but we can get some of it out, right, which means we burn a little bit less fossil fuels, right? And that means that we have a benefit by using the stuff we've already paid for. So when we talk about regeneration, right, the limiting factor here is the temperature of the exhaust gas. Okay, I'm going to tell you a bit of a story. Okay, when I was an undergraduate, I went to school in Canada, not too far from Toronto, and a buddy of mine lived in Toronto. Right, and one night we went up to his parents' place, and we kind of went out on the town, right? And when we got back, it's like 2 or 3 in the morning, and we're thinking, what would be the best right now? One of those McCain frozen pizzas, right? So we put it in the oven, right? Preheated the oven, put it in the oven, and then we fell asleep. So when we woke up in the morning, my friend's daddy comes down the steps. He's like, what the heck did you guys do? What is this, like, charred brick in the oven? And we're like, oh, we're so stupid. We forgot to eat the pizza, right? But that pizza could only get to the temperature of the oven, right? Because heat only goes from high temperatures to low temperatures. And the oven, it has a set temperature, right, that it gets to. And now it fluctuates a little bit, right, as the heater goes on and off. But it's got some maximum temperature in there. And the pizza couldn't heat up past that, even though we left it in all night, right? So this is the same thing. We have this exhaust temperature that comes out of my turbine. And I can preheat the fluid that comes out of the compressor before it goes into the combustor, but never past the temperature of the exhaust gas. Because it's kind of like the temperature inside the oven. Right? We can't get past that. And actually, we don't get quite as far as that temperature. Now, without regeneration, we would have had to add heat all the way from state 2 to state 3. Right? So my heat transfer in would be m dot times h out minus h in. Or heat rate in divided by mass flow rate is going to be h3 minus h2. But if I let my exhaust gas preheat this fluid from state 2 to state X, right now I'm only adding heat to get from state X to state 3. Right? And because the temperature at X is higher, the enthalpy is higher, so this enthalpy difference is smaller. So I'm burning less fossil fuels to get the same benefit. But it's not that I'm getting this for free, right? It's that I've already paid for this heat. I'm just getting it back, you know? So, you know, we were just wasting it. So now we're saying, well, why don't we use it, put it back into our system, right? Like many environmentally friendly options, really what happens here is that we're taking the waste product of something and turning it into a benefit, right? So if I did a first law analysis on this regenerator up here, right, we would see that what's really happening is that I'm transferring heat from this hot gas, right? So it's coming in at state 4. The hot gas, the exhaust, cools down from state 4 to state Y, but the cold gas heats up from state 2 to state X. So it's nice. My exhaust temperature is a little lower, so I have a little less impact on the environment, right? But I'm preheating this fluid, so I'm burning less natural gas, which also gives me an environmental benefit, right? So this heat that we reclaim from the exhaust gas goes to heat up my air from state 2 in this picture to state X. Now, the maximum temperature that we could go, right, the maximum that this gas could preheat would be is if we could get it all the way up to the temperature at 4, or the enthalpy at 4. Right, so we know that the temperature at X is always less than, or I suppose equal to, the temperature at 4. Right? And because for ideal gases, right, if you go and look it up in the textbook on A22, once you know the temperature, you know the enthalpy, right? And enthalpy increases with temperature. So basically, this means that the enthalpy at X has to be less than or equal to the enthalpy at 4. So we have a new kind of efficiency that we talk about with these Brayton cycles, right? When they have regeneration, we talk about a regeneration efficiency. So the regeneration efficiency is going to be the actual amount of heat that gets transferred to the cold side, that's the side that we really care about, divided by the maximum amount of enthalpy that we could transfer to that cold side fluid. Right? So the biggest amount of heat transfer that we could get through the regenerator would be if we went from state 2 all the way to state 4. Right? So Q dot max is H4 minus H2. It's in the denominator because it's the bigger of the two numbers, and we're talking about an efficiency which has to be less than 100%, right, or 1. The actual amount of heat that we got into the cold side was Hx, H out minus H2, right? So this regenerator efficiency is the actual amount of heat that you transferred to the cold side divided by the maximum heat that you could transfer to the cold side. And the maximum heat you could transfer to the cold side is if this state X went all the way up to T4, right? Even though the pressures are different, if X went all the way up to 4, as long as its temperature was the same, it would have the same enthalpy. Regenerator efficiencies are typically between about 60 to 80%. Just like for Rankine cycles, we can also do reheat in these Brayton cycles. Right? So what happens in a reheat cycle is just like in a Rankine cycle, we split the turbine into two pieces. So we have a high pressure turbine and a low pressure turbine, and in between we add some more heat. We burn some more fuel. Right? So here we go between state 3 and state A. Right? Instead of coming all the way down to state 4 prime here, right? We add some heat in between, and then we go through this second turbine. So as we draw this cycle, what happened is we increased our area inside of our cycle, right? And that means we get more net work. We get more net work because we added more power. We got more power out of this second stage in the turbine than we otherwise would have because we put more enthalpy in the fluid by burning more natural gas. The cool thing here is that doing reheat improves regeneration. Because what happens here is without reheat, my exhaust temperature is 4 prime. But with reheat, my exhaust temperature is higher. Normally you'd think, well, that's bad because I'm just expelling that heat out to the environment. But we're actually going to reclaim some of that heat, right? So because reheat gives us a higher exhaust temperature, it means we can preheat the fluid more before it goes into the combustor, right? So without reheat, we put less heat in to the cold side, right? So with reheat, then what happens is we can preheat the fluid more, assuming our regenerative efficiency stay consistent, right? Which means we add less heat as we move from, if you put state 8, right, is somewhere, or X, I guess we were calling it before, it was somewhere in here, right? So we're putting less heat in from the first combustor, right? Just because I like pictures better than words, right? So without reheat, right, we can maximum go up to 4 prime here, right? And then we add heat from 4 prime to 3. But state 3 stays the same when I do reheat or when I don't do reheat, right? So I'm still heating it up to the same temperature, right? But now, in the maximum case, I can heat it up closer to 3, so I'd put less heat in, right? So adding reheat and regeneration at the same time gives you more value than you might think if you just look at those two things separately, right? This is one of those business kind of words that you might see, right? It's called synergy. The idea of synergy is like the sum of the whole is greater than what you might think by looking at as individual parts, right? So 1 + 1 doesn't equal 3, but it maybe gives you an idea of what happens when you're doing something like this. You get more benefit than you might otherwise think, right? So that part is like Rankine cycles. We can do regeneration. We do it a little bit differently, right? And it's a little easier to analyze, which is nice. We do reheat, right? But then we can also do this thing called intercooling. Now, intercooling is like the compressor's version of reheat. So we're going from 1 compressor to 2 compressors. But what happens is in between those compressors, we cool the fluid down. Because the compressor's kind of fighting a battle here. Because it's trying to push those air molecules closer and closer together, right? That's how you increase pressure. But as it's pushing those air molecules closer and closer together, the temperature is getting higher, right? Which means that Brownian motion, right? The vibration of those molecules is getting higher and higher because the temperature gets higher, right? So it's harder to push them closer and closer together. So what we do is if we just pause in between our compression process and we cool that air down, then there's less of that vibration, which makes it then easier. We put a little less power in to squish those molecules closer together, right? So that's what intercooling is. It's kind of like reheat, but instead of working on the turbine side, we're working on the compressor side. Again, we didn't really care about this in Rankine cycles because in Rankine cycles, the power to increase the pressure through the pump was really, really small. Backwork ratio is like 1%, right? So, maybe you cut it down to 0.8%. Maybe that doesn't matter too much, right? Now, I couldn't find a great picture of this in the textbook, so you'll have to bear with my drawing over here, right? So here on the compressor side, right, we go through this first compressor from 1. Normally, we'd go from 1 to 2, right? But now we're going to go from 1 to C, halfway up, right? Cool it down, and then from D up to 2 prime, right? And again, we kind of added this bleb to the cycle over here. We increased the net power produced by our cycle, right? But we didn't do it by producing more power. Instead, we did it by reducing the total compressor power, right? So remember, the net power is turbine power plus compressor power, which is negative. We made that compressor power smaller when we did intercooling. Okay? So we're increasing this area by reducing the compressor power. Right? So we make it a little easier for that compressor to run by cooling the fluid down. So now we got a big, long problem to do. I don't think I'm going to solve this numerically, but I will walk you through the process. This is a pretty complicated Brayton cycle. So it's kind of like got all the trimmings here, right? So it's got intercooling, it's got reheating, and it's got regeneration, right? And this problem asks us to draw a TS diagram, determine the thermal efficiency, find the backwork ratio, and then to track all our assumptions, which we should always be doing in a problem anyway. Right, so now we're going to go through this problem. So the first thing that it wants us to do here is to draw a TS diagram. So I'm going to try to give myself some space here. And again, the first thing I'm going to do is I'm going to count the number of turbines and the number of compressors. I'm going to take the max, which is 2, and I'm going to add 1. This is a little tricky here because it assumes that this pressure, so doing this assumes that P2, which we think is equal to P3, because that's just a heat transfer process, we're going to assume that that also equals P7, which equals P8. And the problem sort of tells us that because it tells us, oh, there's some compressor ratio on state 1, which is root 10, right? Some compressor ratio from 3 to 4, which is root 10. And then I think it also tells us that we have the same stepping down. Or if it doesn't, I'm going to tell you that now. So I need 3 pressures. I need my lowest pressure, which this tells me is 100 kilopascals. I need my intermediate pressure, which is 100 times root 10, which is 316.2. And then I need my high pressure, which is, again, if I multiply that times root 10, I get 1,000. Which is good because 100 times 10 is 1,000, right? So now I'm just going to work my way through the states, right? I start at state 1. What I do as I go from state 1 to state 2 is a compressor. So a compressor, at least the ideal version here, goes up here to 2s, but the real version is going to go over here to state 2 because I got to go up and to the right. Okay. Then I cool down. Anytime I cool down, it's going to be at constant pressure, but I move from right to left. So state 3 is down here somewhere. Right, that gets me here. As I go from 3 to 4, I could go through an ideal version of the compressor. This would be to 4s, or the real version, state 4. Now there's 2 ways that I heat. The first through the regenerator. That's going to get me to state 5. And then through the combustor from 5 to 6. I never draw this very well. So let's go. I think I gotta, because what I want is my exhaust temperature's got to be higher than my. So I'm gonna slope this up more. All right, so that was 100 times root 10, 316. All right, so now I have my ideal turbine from 6 to 7 would be vertically down. We'll pretend that's vertically down. That's 7s. The real turbine is over here to state 7. It tells me that I heat all the way back up to this same temperature here. So now this is state 8 at constant pressure heat addition over here to state 8. And then this is my exhaust temperature over here. I come down even further up maybe to this is state 9 S down here to state 9, and now I get some exhaust temperature down here, which is state 10. I like to draw what's going on, right? So this is W dot compressor 1, W dot compressor 2, W dot turbine 1, W dot turbine 2. I'm getting rid of heat in my intercooler. I'm not going to add this heat because I want to make sure that I don't put it into my thermal efficiency. So I'm going to remember that that comes for free. And this is Q dot of my combustor. This is Q dot reheat. So this is funny, but oftentimes, if I'm going to mess up on a reheat cycle, it's because I forget that you add heat twice. So I got to remind myself it's called reheat for a reason, because you add heat twice. So that's my TS diagram. And if you look through the notes in this lecture here, I go through and construct this through the notes too. So it's all there. And I think in the textbook, or in the notes, I think I talk about how to fix all these states with cold air standard and with air standard. But I think I'm just going to talk about it with variable specific heat, since we did the last one with constant specific heat. So now what I want to do is I want to get I want to get symbolic solutions now. Isentropic efficiency, or thermal efficiency, sorry. C is backwork ratio. Right? So when I talk about thermal efficiency, this is going to be energy benefit divided by energy cost, which is going to be the sum of all my turbine powers, which are positive, plus the sum of all my compressor powers, those are negative. And then I divide that by the sum of all the places where I add heat. So this is going to be W dot turbine 1 plus W dot turbine 2 plus W dot compressor 1 plus W dot compressor 2 divided by Q dot of the combustor plus Q dot of the reheater. Right? So I could see that up here when I draw it, right? Or I could look at the component diagram too. But I have 4 components of work, right? And I have 2 heats in that I'm worried about. Right? To get these, I need my first law. It's an open system. So dE by dt is equal to Q dot minus W dot plus the sum M dot in, H in plus V in squared over 2 plus GZ in minus the sum of M dot out, H out plus V out squared over 2 plus GZ out. All of my components are going to be at steady state. They're all one inlet and one outlet. At least all of these 5 components here. I'm going to neglect kinetic energy changes and potential energy changes. So that's going to go to 0. So then I'm going to say for turbines and compressors are adiabatic. That's going to tell me that W dot is equal to M dot times H in minus H out. And if I'm talking about a combustor, it's going to be passive, which means that Q dot is going to be M dot times H out minus H in. Now I'm going to sneak this picture down over here so I can just remember what state numbers go where. So when I talk about my thermal efficiency, the first turbine goes from state 6 to state 7. It's always the whole mass flow rate, so I don't have to do the whole colored pencil thing we did with Rankine regeneration. So there's only one mass flow rate, because if I did dm by dt is equal to the sum of m dot in minus the sum of m dot out. They're all steady state, one inlet, one outlet. M dot in is equal to m dot out. And because we don't split the mass, there's only one mass flow rate. So this is H6 in minus H7 out. Oops. Plus my second turbine, m dot times 8 to 9, H8 minus H9. Plus my first compressor, m dot H1 minus H2. I expect these first two to be positive and this one to be negative. My second compressor, m dot H3 minus H4. Divide all of this by the two places. Remember, it's reheat. I'm telling myself that because often for me, I'm like, oh, good, I got all the turbines and the compressors. I feel like I'm on the home stretch here, and sometimes I forget that we have this reheat combustor. So it's out minus in. So this is going to be H6 minus H5 plus m dot. Second combustor is H8 minus H7. All the mass flow rate factors out of the numerator and the denominator. So this is going to be H6 minus H7 plus H8 minus H9 plus H1 minus H2 plus H3 minus H4, all divided by H6 minus H5 plus H8 minus H7. And because it's variable specific heat this time, that means that I don't get to cross that stuff out and just go with temperatures. If I want the back work ratio, this is going to be the sum of the compressor powers divided by the sum of the turbine powers. Right? So the compressor powers, this is m dot times H1 minus H2. And I guess we take the absolute value of this because otherwise it would be negative. Plus m dot H3 minus H4 divided by m dot H6 minus H7 plus m dot H8 minus H9. And again, the mass flow rates cancel. So we got our symbolic solutions, which is great, right? But there's like 9 unknowns that we have here. Often, this question too might ask, what is T exhaust? So what's the temperature at state 10? We don't know. So now we have the exciting task of fixing the states. Right? And this one gets long, right? You're never going to see a problem like this on an exam where you have to fix where the state because this looks like 10, but it's not really 10 because there's real outlets to all the turbines. That's 2 turbines and 2 compressors. So it's really 14 states, right? And you're never going to get a state table that's this blank, right? We'll see there's a lot of repetitive work that happens here. But if you could solve the problem when the state table is this blank, and then it doesn't matter how much I fill in later, right? Because you just can do this, right? So we will start with state 1. State 1, we know temperature 1, and we know the pressure at 1. This is variable specific heat, so we actually need H, right? And we're also going to want the VR or the PR values. Because I'm just going to write a note to myself that if delta S is equal to 0, I need to use an isentropic relationship. Now, we saw before that if it was constant specific heat, that would be T over T is equal to P over P to the power of K minus 1 over K, right? If it's variable specific heat, then it's going to be P over P is equal to PR over PR. If you want these equations, right, then you come over here and you say, oh, look at the equation sheet. For ideal gases, we're looking for isentropic ideal gases. We want K in the exponent if it's constant specific heat. We want a pressure ratio. We want PR over PR or VR over VR. But here, because it's an open system where we know the pressure ratios, then we're going to want this P over P is equal to PR over PR. So what do we do with this, right? So the nice thing is, because I know T1, everything else is beautiful. Here, oh, I guess first, we're going to say we're not doing constant specific heat here. We are doing variable specific heat here, right? And this would be like 1 over 2, PR1 over 2. So that they line up, right? That's on the equation sheet. Now, it helps when we're thinking about variable specific heat, because I'm not going to do all the numbers here because it would take a long time. But it helps to remember what table A22 looks like. Oh, let's see. So if you do need specific heats, right, they're on this table A20, right? Air, CP, usually around 1. Right? But A22, right, looks kind of like this. There's temperature, H, U, S, superscript 0, PR, and VR, right? And then repeat it on the other side. So I just need one thing. So typically, what I'm looking for is, you know, if this is my table A22, there's temperature, H, U, S superscript 0, and then it says, oh, if delta S is equal to 0, then you can use PR or VR. The thing that I'm looking for usually is I want a temperature or I want PR, right? But in this case, they told me the temperature, right? So for state 1, I know T1, so that means I can come over here and I can get H1, and I'm going to get PR1. That part makes sense? So now I want to go from state 1. I would like to go right to state 2, but I can't because I know almost nothing about state 2. Although I guess I do know that P2 over P1 is equal to root 10, right? And we worked that out, so that was that P2, because P1 was 100, right? So this was root 10 times 100, 316.2 kilopascals. That's also going to be equal to P2S. But I cannot use, so from 1 to 2, delta S is not equal to 0. So I can't use the isentropic relationship. So I kind of got to make a pit stop over here to go to state 2S first. Because here, delta S is 0. So now what I can do is I can say that PR2 over PR1 is equal to P2 over P1, which is equal to root 10. So PR2 is equal to root 10 times PR1. And that gives me PR2, which is good because at any state, what I'm trying to find is either T or PR, right? At least if it's an ideal state, right? Those are the things that I'm looking for, right? So now what I would do is so now we use this isentropic relationship to go from PR1 down here, and we found PR2, right? Because delta S was equal to 0. Now we can go back, interpolate this way, and get H2S. Does that part make sense? So if, for example, right, if we were on this table, and let's say my T1 was 300 degrees, right? I don't know what it actually is in the problem. 300 times root 10. Oh, no, that's not what I do, right? Because now 300 would mean my PR value is 1.386. So I take 1.386 times root 10, and that gives me 4.38. So now I'd look over here. Oh, no, PR 4.38. So it's going to be somewhere in between these two. So I'd find that value, and then I'd have to interpolate backwards over here to find H. Does that kind of make sense? We're going to do a lot of that in this problem, right? But now that I have, so this gives me H2S, which is great, right? Maybe over here for state 2, now I can go back to state 2, right? So now I say, oh, state 2, that's the real turbine outlet. Oops. Real. Which means I can use the efficiency of my turbine, which is W dot real over W dot ideal. Right? Which means that M dot H, oh, this is a compressor, I'm sorry. And because it's a compressor, it's the ideal over the real. Right? So this is going to be M dot times H1 minus H2S divided by M dot times H1 minus H2. The mass flow rates cancel. And in this problem, they probably told us the isentropic efficiency because they didn't tell us about state 2. I guess because they probably didn't actually give us enough information. Oh yeah, no, so here they said that the efficiency of the compressors, the turbines, and the regenerator are all 0.8. So here in this problem, we know the compressor efficiency. We now know H1 and we know H2S. So I'm just looking for H2. So here I get that H1 minus H2 is equal to H1 minus H2S over the efficiency of the compressor, or that H1 minus H2S over the efficiency of the compressor is equal to H2. And now I fixed that state. And because I'm not going from state 2 to another isentropic process, I don't have to interpolate at state 2 to find PR2. Right? So the important thing to remember here is that we knew the temperature at state 1. So we used that temperature to find H1 and PR1. And then I said, as I go from state 1 to 2, where is the isentropic process? It's actually not state 1 to state 2. It's state 1 to state 2S. And then so I used my isentropic relationship to fix state 2S because I knew the compressor pressure ratio. And then once I knew state 2S, then I could use the compressor efficiency to find state 2. the reason this wouldn't be a great exam problem is now we're going to do essentially the same thing all over again. State 3 is like state 1 in that I know T3 and I know that P3 is equal to P2, which was equal to, what did we say, 316.2. But because I know T1, now this is, or T3, this is just like, right? So now I'm going to go to table A22. I'm going to find H3, and I'm going to find PR3. Now, because I've done this before, I'm going to go from state 3 to state 4s, right? And I say, oh, is this isentropic? Yes, it is. And it's variable specific heat. So I'm going to say that PR4 over PR3 is equal to P4 over P3, which again is equal to the square root of 10. So from here, PR4 is equal to root 10 times PR3. This gives me PR4. I like having any property that's on the table for A22, because once I know one of those things, because it's an ideal gas, if it's on that table and it's one of the things I know, it means I can find everything else. So now from PR4, I'm going to go to table A22, and that's going to give me H4S. Now I can go to state 4. Again, I'm going to use the compressor efficiency. This is going to be my ideal compressor power divided by my real compressor power, right? Or m dot times the ideal would be H3 minus H4S divided by m dot H3 minus H4. The thing that I'm trying to find here is H4. And now I know H3, I know H4S, and they told me the compressor efficiency. If you went right from state 3 to state 4, you might get to this equation and say, I don't know H4 or H4S, in which case, hopefully that's a cue to you to say, oh, I need to go back and find H4S, so I need to go from 3 to 4S because that's the isentropic process. Another way this problem could be asked is instead of giving us the compressor efficiency, I could tell you the temperature at 4, make state 4 like state 3. And then I could ask you what the compressor efficiency is. And then it's this same equation. It's just a different permutation of the things you know and the things you don't know. Right? So just like this is going to be this same equation that we had here, right? But it's going to be, well, I can just manipulate it again because the screen doesn't really like to move around. My computer's like 8 years old, so I need a new one. You can email my boss. Right? So this is going to be H3 minus H4 is equal to H3 minus H4S over the compressor efficiency, or H3 minus H4S over compressor efficiency is equal to H4. Now we have H4. This next one is the tricky one, or one of the tricky ones. As I go from 4 to 5, when I look at my picture, it doesn't like rendering all the pen strokes. Maybe because my pen strokes are so messy. Right? It's funny because my kids are learning how to write by hand, and they still have to learn like calligraphy and stuff, or not calligraphy, but cursive. But my penmanship was always terrible, so they get nothing from me, right? I'm also not a good speller, so that is something they inherited from me, unfortunately. You know, when I was a kid, my buddy Matt and I, in like grade 3 and grade 4, you know, they'd give us spelling tests, and we would always race to see who would get it done faster, right? But there was no points for like efficiency, no points for getting it right. It was just all about how fast you could do it. I think that's why I'm terrible at spelling, right? Okay, so now we're going from 4 to 5. That's like through this regenerator, right? Now, there's a couple things we know here, right? One of them is this new thing called regenerator efficiency, right? And they told us what the regenerator efficiency was, right? They told us that that's 0.8, right? And that this is Q dot into the cold side divided by Q dot cold max. And that the maximum that this can go, and I maybe didn't draw this great on my TS diagram, but it's this exhaust temperature 9, right? That state 5 can only be pushed as high as state 9, right? Because that's the original exhaust temperature, right? But then we cool it down to 10, right? So we're going in the regenerator from 4 to 5, but the maximum is if we went from 4 to 9. So here, heat transfer is still going to be m dot times h out minus h in. M dot h out is going to be h5 minus h4 divided by m dot times h. What are we doing here? This is, if the outlet was the same as state 9, then this is what we would do. There's good news and bad news here. The good news is that we have a symbolic solution, and that I know 3 of these things. The bad news is there's 2 things I don't know. And even though I'm not a mathematician, I know that if you got 1 equation and 2 unknowns, it means that you're in a problem that you can't yet solve. So I'm going to skip it, right? And the nice thing about these problems is that if you get to a point like this, look for the next place where you have a given temperature, right? So here at state 6, they tell me the temperature at state 6. Right? So it's nice that it's the next one too, because that suggests that this is not a bad place to start skipping. Right? So now I'm going to skip and come back, but for now I'm going to move to state 6. Now when I think about these problems anyway, I go back to my TS diagram. And this is good news. Because we're basically, once we're at state 6, it's like we went all the way up the cycle already. Now we just got to come down. And going up was through a bunch of compressors. Coming down is through a bunch of turbines. So the strategies are pretty similar, right? It's just now we got to go through these turbines instead of compressors, right? So the nice thing about Brayton cycles is they will usually tell you the temperature at the top of the mountain here, right? The highest temperature. Sometimes they're a little tricky about it in that they don't say, oh, the temperature at state 6 is something. Sometimes they'll tell you the maximum temperature in the system is something, right? So then you have to know on your TS diagram, where's the maximum temperature, right? So here T6 is known, and P6 is equal to, because it's only pressure, right? So this is equal to P4, which is equal to P5, which is equal to 1,000 kPa, right? Because we took 100 and multiplied by root 10 twice. This is great because I know the temperature. Anytime I know the temperature, I'm going to go to table A22, and I'm going to pull out H6, and I'm also going to get PR6. So as I move from 6 to 7, that's the first turbine. But because I got an isentropic efficiency for my turbine, first I'm going to go to 7s, right? And here delta S is equal to 0. This is an ideal turbine. Now, that means that I can use my isentropic relationship, the same one that I've been using through the whole problem for variable specific heat, PR7 over PR6, because this is the isentropic relationship. I put the one that I want on the top, is equal to P7 over P6. And here, I don't know that it's explicitly stated. If we gave you a problem like this, we would tell you, I think a little more explicitly than in this problem, what these pressure ratios are. But here we assume that the middle pressures are all the same. So this is 1 over root 10. Right? So then here we know that PR7 is equal to PR6 over root 10. Right? Which means that I know PR7, and I can go back to table A22, right? Notice these arrows go the same way, right? If I know the temperature, then I'm interpolating from left to right. But if I know PR, then I'm interpolating from right to left, right? So now I'm going to get H7S. Now I'm going to come to from state 7S to state 7. Right? This is going to be the real turbine. So I can use the isentropic efficiency of the turbine, which is still going to be power over power, but now it's the ideal that produces more power than the real. Right? And this is going to be m dot H6 minus H7 divided by m dot H6 minus H7S. These mass flow rates are going to cancel. Again, the thing that I don't know is this, but I know all the rest of these things. So H6 minus H7S times my turbine efficiency is equal to H6 minus H7. So H7 is equal to H6 minus the isentropic efficiency of the turbine times H6 minus H7. Now I know H7. I don't have to go through and find PR7 because the next process, as I go from 7 to 8, if I look at this, this is the reheat process as I go from 7 to 8. So because I'm not going through an isentropic process next, I'm never going to have to find, I don't care what PR7 is, not PR7S. So I don't have to re-find the PR at the real outlet, right? Just like I did in the compressors. So now this ends up being just like, remember how when we went through the compressors, it was like a repeat when we did the second compressor? This is the same thing, right? So now here we know T8, right? Because as we go from 7 to 8, this is still, and then we know that P7 is equal to P8, right? And because I know T8, I can go through on table A22, and I can find H8, and I can find PR8. The states where they tell you the temperature, those are my favorite states. Now as I go from 8 to 9, it's a turbine again, right? So I want to go 9S first, right? Because delta S is equal to 0, which means that PR9S over PR8 is equal to P9 over P8, which again is going to be 1 over root 10. PR9S is equal to PR8 over root 10. Once I have this, I can go to table A22 and I can find H9S. Which means we're almost done, right? So now I want to find state 9, right? This is the real turbine. So I want to use my isentropic efficiency for the turbine. This is going to be that the real power is less than the ideal power. This is going to look very much like this equation, right? H9 is going to be H8 minus the turbine efficiency, H8 minus H9S. Two things I can do now. Well, let's do the first one first. Right, so remember how we skipped state 5? Because when we did state 5, we didn't know state 9 yet. Right, but now we know state 9. So now I can go back to state 5. Now we know H9, right? So now I can go through and find H5, right? So here, H5 minus H4 is going to be equal to the regenerator efficiency times H9 minus H4. Or H5 is going to be H4 plus the regenerator efficiency H9 minus H4. For this particular problem, that's all that they've asked us to do, but I do want to show you one more thing. Because they could ask us for the new exhaust temperature, which is state 10. Instead of jumping around, I'm just going to redraw this, right? So here is my regenerator. I have state 9 coming in here, and I have state 10, that's the exhaust. And then coming out here, I had state 4 going into the regenerator over here, right? And state 5 coming out into the combustor. So we know that there is heat transferred from the exhaust gas into the preheated fluid, right? So I'm going to draw a control volume, right? Because this problem didn't ask this, but it's the kind of thing that you might see in the textbook or on the exam. So what is T10? Do the first law. When you don't know what to do, try the first law. On the regenerator in this case. Because regenerator efficiency won't help us. Because the regenerator efficiency only tells us what's going on between 4 and 5. Right? So here, now we can say dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in plus V in squared over 2 plus GZ in minus the sum M dot out, H out plus V out squared over 2 plus GZ out. For the regenerator, steady state, even though there's heat going from the hot side to the cold side, we're going to say none of that crosses the boundary of our control volume. So it's adiabatic, it's passive, no fan blades, no kinetic energy change, no potential energy change. So we're going to get that 0 is equal to the sum of M dot in, H in, minus the sum of M dot out, H out. I like to break this down into hot side and cold side, but the nice thing is here, there's still only one mass flow rate because this tube is all chained together in series through all these different components, even though it goes through this component twice. So here I'm going to say M dot on the, let's say, cold side. This is going to be H in minus H out, so H4 minus H5 plus m dot on the hot side, H in is state 9 minus H out is state 10, right? But these mass flow rates are the same, so that part cancels out. So now I can get that 0 is equal to H4 minus H5 plus H9 minus H10. The thing that I'm trying to find is H10, right? It's going to be H4 minus H5 plus H9. Now, once I have H10, the problem actually asks me what the temperature is, right? So now I can go to table A22, and I can find T10. So this problem's long. I think that some people sort of view a problem like this as being, so far I've said I think the Rankine regeneration is the hardest of the problems that we've done. This one gets to be pretty long when you have to do the whole thing. When it's, when it's reheat and intercooling and regeneration, and you got to do all of this stuff together, it's kind of tedious. But remember, if you see a complicated thing like this on the final exam, it's you're not going to have an empty state table like this, right? I'm not going to make you go through 2 compressors and 2 turbines, right? Because it's kind of a waste to have you repeating all that work, right? Because once you've demonstrated that you know how to do it once, why do I ask you how to do it twice, right? So the state table would be much more filled in, right? But even if it wasn't, if you know how to do it when it's this blank, then that means it doesn't really matter which blanks are there and which parts are filled in if you know how to do all the parts, right? So here, it's the key to unlocking these particular problems is usually knowing where the isentropic processes are. Then you're looking at the isentropic efficiencies to find the real exits of compressors and turbines. You need the regenerator efficiency to fix state 5 in this case. But sometimes you have to skip that if you don't have the exhaust temperature, right? But you just go to the next place where you have a temperature, and then you come down through the turbines. Once you have that, then you can go back and fix state 5 once we had state 9, right? So 9 gave us 5. You can tell when I'm doing this with the mouse. Hopefully, anyway. Hopefully that looks worse than when I do it with the pen. And then you can do the first law on the regenerator to get the exit temperature or the exhaust temperature. So that is all the material that I had for you that's new. But I'm happy to stick around if people have exam type questions. So does anybody have any questions? Yep.
Yeah, I do. Can we look over? So I just have one question on the quiz that I actually not
Maybe
sure
you
how to
can
do.
explain the problem to me and I'll talk through it.
Let's see. Where is it? I just lost it. Wait, where'd it go? I might have clicked it out for by accident. I just know it has to do with the nitrogen. Oh, found it. So the question said nitrogen gas passes through an insulate diffuser at a steady state. The inlet velocity is 1,000 feet per second, and the outlet velocity is 10 feet per second. The inlet temperature is 290 R, and it asks what's the temperature at the exit of the diffuser in R.
Okay.
So yeah, try doing this.
Yeah, so
I don't know.
we're going to get to know kinetic energy a little bit better next class, but it's still important because it's an open first law problem, right? So what a diffuser does, right? So a nozzle looks something like this, right? So you reduce the area, that makes you get more kinetic energy at the outlet than the inlet, right? A diffuser is the opposite, where it looks like this, where the area is expanding so the velocity goes down. So here, what we're expecting is for H to go up and for kinetic energy to go down. So that's the energy transaction that a nozzle does, right? So dE by dt is equal to Q dot minus W dot plus the sum of M dot in, you 2 joules, H in plus V in squared over, now, because it's imperial, it's 2GC plus G over GC, Z in, minus the sum of M dot out, H out plus V out squared over, again, 2GC plus G over GC, Z out. Now, for the diffuser, we're going to say that it's steady state, that it's adiabatic, that there's no fan blades, that there's one inlet, one outlet, and no potential energy change. Anytime kinetic or potential energy sticks around, you know, the hair on the back of your neck's got to start standing up, because units are going to be a problem, especially because this is an imperial problem. So the first thing that people sometimes fall down on is they forget to divide by GC here. Right? I guess the companion to this equation is going to be that dm by dt is equal to the sum of m dot in minus the sum of m dot out. But we said it's steady state, one inlet, one outlet, so m dot in is equal to m dot out, so just m dot. Right, so this is going to be 0 is equal to the mass flow rate times H in plus V in squared over 2GC minus H out plus V out squared over 2GC. And you can see the mass flow rate is going to cancel, and this is what we were talking about here, right? So what's going to happen is, or we could rearrange this. Maybe we make it even a little bit cleaner to see this. H in minus H out plus V in squared minus V out squared over 2GC is equal to 0. You would get the same equation for a nozzle. But what happens in a diffuser, so for a diffuser, we expect enthalpy to go up, right? So we think that H out will be bigger than H in. So we expect this to be negative, right? And so we expect the kinetic energy to go down, which means that this term is going to go down. So conceptually, this so far agrees with our understanding, but it's going to get tricky. So there's two things. Let's say because they told us that we want a temperature, I'm going to say, and because it's a multiple choice question, so I don't know what method you're using, so I'm going to say constant specific heat over here, which means 0 is equal to Cp times T in minus T out plus V in squared minus V out squared over 2GC. But ultimately, if I look this up in the textbook, this whole term is going to be in BTU per pound mass, right? Because Cp is going to be in BTU per pound mass Rankine, right? And this temperature difference is in Rankine. Even if it's in Fahrenheit, the delta is the same, right? But when I do this is where our problems begin. Feet squared per second squared is in the numerator, right? Because it's velocity over velocity squared, sorry, right? So now GC is a funny unit because it's kind of like an acceleration. So it's kind of feet per second squared. But then it's also, if I wrote down Newton's second law, right, I would see that weight is equal to mass times gravitational acceleration. And this works great in the metric system, or in imperial, right? Because I'd get weight in newtons, and this would be in kilograms, and we can see that there's a way to, or kilograms and times either newtons per kilogram or in meters per second squared, which is the same thing, right? But here, they made it so that 1 pound mass, or 1 pound force, is equal to 1 pound mass times G, which is 32.2 feet per second squared, right? So again, I'm not a mathematician, but I know that 1 doesn't equal 32, right? So instead, we have to take this and divide by GC. Now, what's GC? It's kind of like an acceleration. So it's 32.2. So its magnitude is the same as the gravitational acceleration here on Earth, right? So that would cancel out the feet per second squared. It cancels out the 32.2. We're looking pretty good, except that this says 1 pound force is equal to 1 pound mass. But that doesn't work that way, right? So it's also pound mass over pound force. This now cancels, and we get 1 pound force is equal to 1 pound force. So this is pounds mass over pounds force. Now, you don't have to memorize that because it's on the equation sheet. Right? GC is equal to 32.2 foot-pounds mass, or if you like, feet per second squared, times pound mass over pound force. Now, what do we do with these units, right? So, feet per second squared, I get rid of one of these feet, get rid of the second squared, right? And now what I have, this is equal to foot-pounds force per pound mass. That's okay, because at least it's the right quantity. It's energy, foot-pounds, force times distance, over pound mass, right? And this is also energy per unit mass. It's just not the right kind of energy yet. So I now got to multiply this by 1 BTU. I can come over here again to my equation sheet. And it says that 1 BTU is equal to approximately 778 foot-pounds force. So this is 1 divided by 778 foot-pounds force. Right, so now the foot-pounds are going to cancel with the foot-pounds. I'm going to get BTU per pound mass. So the unit conversion here is a pain, right? And then you got to look up CP. If I was looking up CP, I would go back to that table A20. It's nitrogen. So I would just pick, I can't remember what temperature they gave us. They gave us the one temperature, right? Was it 300 or something? Yeah, so I would just, let's say it was 300.
I think 200. Wait, I think
it told us one temperature, but not the other.
The inlet temperature is 290.
290?
Yeah. Yeah, 290.
I would probably just take the number at 300. You
okay.
could interpolate, but here you can see that the interpolation of CP between 250 and 300
makes
is
a
the
difference.
same.
Okay.
And really at 350, it's about the same too. So as long as our temperature is not wildly different, right? Here, this is fairly constant, the specific heat. This is going to be, what did we say, 1.04 BTU per pound mass Rankine. Right, so now I know this. I know the inlet temperature. I don't know the outlet temperature, but I know these two velocities, and I know GC. So I could use this equation now to solve for T out. Right, so this is going to be T out minus T in is equal to 1 over CP times V in squared minus V out squared over 2 GC times 1 over 778 BTU per pound mass. Or if I'm just looking for T out, it's going to be T in plus A, where this part here is A. Does that make sense?
Okay, a little bit.
So this is definitely a kind of thing that a lot of people make mistakes on. It's super easy to make a mistake on this kind of problem because you got to remember to divide by GC. You got to remember all this ugly unit conversion stuff. And even if it's a metric problem, you have that same unit conversion stuff. if you had to do this for variable specific heat, then you would keep this, you would solve for H out, and then you would go to table A, in this case 22E, and then find, you'd have to interpolate, so you'd get something like, I'm just going to make this up, but let's say that, I don't know, let's say that, oh, the wrong table. Right, we came in at 290, so let's say that, I don't know, we went out at 310 or something, right? So then we would say that, H we got was 310.24, so then I'd have to interpolate to find, or maybe it's 307, and I'd say, that's equal to 307 Rankine. Does that kind of make sense? I just made up numbers. I don't know what the real number is, but.
Just calculating it, see if we can get the answer.
CP is about 1. So you could, on a multiple choice, you could just sort of look at this and see what the thing is. Just remember the sign is different. So here we expect T out to be bigger than T in. So if you did this, let's see what the numbers are. So V out is 10 squared minus 100 squared, right? This looks like a huge number, right? But first we got to divide by 2. Then we divide by GC. 32.2 is the magnitude. Then we divide by 778, right? And we get that it's 0.2 degrees higher. Is that true? Did I do it right?
Well, the answer is 370, so I'm trying to get there.
The answer is 370, so that means let's see again. So maybe there's a mistake in the thing. So it's 10, because I did 100. 10 squared minus 1,000 squared. Or is it the other way around? It's in minus out, so I got 1,000 squared minus 10 squared divided by 32.2 divided by 2 divided by 778. So I get that the temperature difference is 20 degrees. Does that give you the right answer? 290 plus 10 is plus 20 is 310.
That's not. It said 370. It said 370.
So maybe there's a mistake in the problem, or maybe I did something wrong here. But if CP is just 1. Yeah, it sent me the question because maybe the answer is incorrect.
I'm not sure.
Because the process here is correct. It's interesting. So what if we did 20 times 32.2? They said it's 370?
Yeah, that's the answer. Yeah, that's the answer, 370.
370. And the inlet temperature was 290, is that?
Yes. Yes.
So they're off by a factor of 4. The delta. But I think there may be a mistake then in the quiz.
Because when I look at this question and try to solve it, I couldn't really get the answers. So I just kind of like, well, it can't be 290, and it can't be lower than that.
Yes.
And I usually like to pick the second highest number, because it usually works in every quiz. So I might as well pick 370.
Well, it is helpful on a multiple choice if you can eliminate some answers that are obviously incorrect. It does seem like maybe there's a problem with this question, though. So if you send me an email about it, I'll double check it myself. And if it's different than what we're saying here, I'll tell you why. But I think that the delta should only be 20. So I think that the answer is wrong. But I might do it again with variable specific heat to see if we get a number that's dramatically different.
Oh wait, can you scroll up a little bit?
Did I forget a factor of 4 somewhere?
It's saying nitrogen gas. I'm not sure that plays.
Maybe we looked up the wrong value for CP. CP for nitrogen though, because air is mostly nitrogen, right? So it's still, and we looked it up at 290, right? Like you're not going to get a factor of 4 out of that, right? Like it's not even on the table if it's.
Yeah, it's air because I was wondering because it didn't say like air, it said nitrogen, so I don't know how different the value.
I think maybe it's just trying to get you to look in the textbook to see what the CP value is. Oh, but you know what? I'm looking on the wrong table because this is the metric version of the table.
Oh, is that?
That could be the problem.
I was like, wait. Oh, it should be. Oh man, I love numbers. It's a lot of numbers here.
Yes, so that's where our factor of 4 comes in. So it is correct. So 290 and 300. So this should be about 0.25, right? So we were using CP as 1, right? When this was 1, and so this part here we saw when we did the math. This part here has a magnitude of about 20 Rankine, right? But then this, well, I guess it doesn't make sense talking about in units, right? But this is not 1, but 0.25, right? So here, if we take, what was it, 1,000 squared minus 10 squared divided by 2, divided by 32.2, divided by 778. Oh, I screwed something up. 1,000 squared minus. So if this was a test, I like to break different parts down when I'm doing it on paper, and because I'm really good at putting stuff wrong into my calculator. Squared divided by 2 divided by 32.2 divided by 778 is 20. But now I divide that by 0.25, and I get that this A is equal to 80 approximately Rankine. And this was 290, so then this is approximately 370 Rankine. So the problem was that I looked up the wrong value of CP, so I tried to do it too fast.
Quick question. How can you pick? Wait, so how do you get CP again?
So there's some judgment that happens here, right? Because so in this case, like 200 is this, so I'm picking a number close to the inlet because that's the temperature we know, right? We could check because 370 is, so it's going to be between, so 290 is something like 0.25. The final answer we could check, was 370, so it's less than 0.251.
Wait, but isn't it the temperature in R in the question, not F?
Yeah, these are,
Because it's in Fahrenheit. But
so then we'd have to take this number and it's a good thing that it doesn't change very much, right? So we have to add 460. So you said it was 290 F?
290 R.
290 R.
It's in R.
So we'd have to take 290, right, minus 460. So we get minus 170. I don't even know if that's going to be on our table. Let's see.
Yeah.
But we can see that this number doesn't change too much, right? And that's the thing. Once you're sort of employing this constant specific heat, so yeah, our number is going to have some uncertainty with it, but it gives us a ballpark, right? And that's the ballpark we're looking for on the thing. If you wanted a more accurate answer, then what you can do is you can come down here and you can say, 290 Rankine, which actually isn't even on the table. So you don't even have an option of doing that, right? But if 290 Rankine was on the table, then you would do this, right?
I think that's like the one that actually really got me confused is when I try to convert that to Fahrenheit and it's below the temperature, like in the given chart. So that's why I couldn't really find an answer. Okay,
No, that's
so
good.
I understand now.
Did you have any other questions?
I'm just looking through the rest of the quiz.
Vidra, did you have questions?
So I have another question. Not sure about none of this. I don't remember. So this is in the same quiz. It's in 2B. It's question 5. It said an incompressible liquid enter into a rigid pipe with diameter of 1 feet at 1 feet per second.
Sorry, can you say that again?
After traveling,
I missed it.
so it said an incompressible liquid enters into a rigid pipe with a diameter of 1 feet at 1 feet per second. Okay. And it said after traveling some distance through a network of pipe, the same liquid exit in the pipe with a diameter of 18 inches. Or 3 feet if you want to convert that really
Diameter is
quickly.
equal to 3 feet?
Yes. It said here 18 inches, but let's convert
So it's
that
18-inch radius? And the other one?
Yes. No, diameter. They both
18
diameter.
inches is 1.5 feet, right? 12 inches per foot?
Wait, did I do that?
Yeah,
I
that's
might have
okay.
converted wrong then. Wait. Okay, well, just to continue, the system is at steady state. What response best describe the exit velocity in 18 inches diameter
So now,
pipe?
this is a conservation of mass problem. So dm by dt is equal to the sum of m dot in minus the sum of m dot out. But we know that it's at steady state with one inlet and one outlet. So m dot in is equal to m dot out. There's really only 3 ways that we know how to find mass flow rates. Area times velocity over specific volume. Or we can look for some place with more than one inlet, more than one outlet, and do the first law. Or we can look for some place where we know the power or the heat transfer and do the first law. These 2 are off the table, but because they give us enough information to find the area, that's probably pretty good. So this is going to be area, so this is pi d squared over 4, d1 squared, times velocity at 1, divided by the specific volume at 1, is equal to pi d squared at 2 over 4 times v2 squared over specific volume at 2, or that v2 squared is equal to, why am I squaring the velocity? I'm too used to the first law. So v2 is equal to v1 times the specific volume at 2 over the specific volume at 1 times pi over 4 d1 squared over pi over 4 d2 squared. All right, that goes away. Here, do they tell us anything about the temperatures?
No.
I'm going to assume
No.
the temperature is approximately constant. Since V is about VF at the temperature. I'm going to assume, because I don't see any information to calculate this, I'm going to say this is approximately 1. Right? And especially for liquid water, the density of water is always about 1,000 kilograms per meter squared, or the specific volume is always about 1 over 1,000 meters cubed per kilogram. So it's probably not a terrible assumption to say that this is about 1, unless you get a really big temperature change or you start to boil, right? If it was liquid to liquid, but it says it's incompressible on both sides, I think, right?
Yes, just say liquid, the same liquid.
V2
So, okay, that makes sense
is
now.
equal to V1 times, I'm going to say 12 inches squared over 12 squared inches squared divided by 18 squared inches squared. The inches squared drop. I could do this in feet or inches. So I think that this should be 12 squared divided by...
That should give the answer. Okay.
Right, so it should be 40%, right? So it should be 0.44 or 0.45.
Yeah. It should be 44. Yeah. Okay. I noticed why I made a mistake on this one.
Well, this one can be tricky, especially if sometimes it'll say saturated liquid enters, right? The area changes and saturated vapor exits. And then the specific volumes are different by about a factor of 1,000. So that can dramatically change what happens too.
Okay, that makes sense. Okay, I see now. Okay, thank you.
Any other? Oh,
yeah, just looking through. I know, like, I usually write notes for
that's a
each
good
of the
idea,
questions.
right? Because that helps you when you come back to study to say like, oh, this was something that I didn't get or something, right?
I think that's about it for now. I think I'll
Sure,
come
yeah, so I'll be
tomorrow
around at 4.
office hour
So,
just in
especially
case I
for that
miss
first
anything.
like 10 minutes or something. If nobody shows up, then I'll probably book. But okay.
Yeah. Alright. So yeah, in case I find any new problems, I guess I'd be there.
Sounds good.
Okay.
Have a good night.
Alright.
Bye bye.
Yep. Thank you.